Hello class, and welcome to section 3.3, which is about transforming linear functions. By the end of today's lesson, you will be able to identify and perform linear transformations. So a transformation is mapping each point on the graph to a new location. So it's taking an original function, an original line that we have, and moving it around in some way on the graph. There are two different types of movements that we're going to talk about. The first is a translation. That's simply shifting a point on a graph the same distance. So if I take this vocab and I shift it to the right or I shift it to the left, that is a translation. All I've done is shift it. Or I move up and right, or maybe down and right. It's just sliding it around the graph some way. These translations can be vertical, horizontal, or a combination of the two. The other thing we're going to talk about is a dilation. So that's increasing or decreasing a graph by a scale factor. So that would be like if I took a shape and made it bigger or smaller on the graph. Or moved it around in some way, shape, or form. I'll explain what that looks like with lines a little bit later when we get to the graphs. So first we're going to talk about translation. A key fact about translations is that the slope of the graph is going to stay the same, but the y-intercept value is going to change. So what that means is when you're looking at an equation in slope-intercept form, so y equals mx plus b, it's not going to change the slope. It is going to change the y-intercept value. If it is a vertical translation, you're either going to be adding to move up or subtracting to move down. So you're going to go up by a certain amount or down by a certain amount. This is changing the outputs. The horizontal translation is going to be changing the inputs. So again, when you add a value on the outside, that's up. Add a value or subtract a value on the outside, that's going to be down. Horizontal is a little bit backwards. When you take away a value from the x, it's moving right. And when you add a value to the x, it's moving left. Why does that happen? So if we're looking at this graph right here, I have this original line, which you can see as I move it. That blue line is going to stay in the original spot. If I move the y-intercept, so I change the v value, and I add 2 to that value, my graph has moved up. If I take that and I move down, subtract 2 from that value, it's going to go down. Now, with the left and right, if I take this point and I shift it 1, 2 places to the right, this green dot is no longer my y-intercept. My y-intercept has shifted down 2 spaces. That's why when you move to the right, your y-intercept value is moving down the graph. That's why it's x minus a k value to move to the right. And then flipping that, if you take and you shift your graph to the left, your new y-intercept is going to be above where it used to be. So we have our y-intercept is now above the graph when it is moved to the left, which is why we're adding on to the x's when we have a move to the left. So, looking at equations, if your original function was f of x is equal to 5x plus 3, and your new function, g of x, is f of x plus 1, notice the slope stays the same. So that's indicating to me that we have a translation going on, and we need to figure out how we got from 3 to 1. To get from 3 to 1, that means you would be subtracting 2. So this would be a move of down 2. So we would have down 2. And then we're going to just put units because that's how we call the measurement on the graph. Looking at the next one, we've got 5 and then in parentheses x minus 7 and then plus 3. So we have something changing the inside the x, and then we have the plus 3 at the end. So the 3 hasn't changed, so our movement here is affecting the x values only. We've got that negative, so with the x's we're going opposite, so negative means move positive. So this is going right 7 units. On the last one, we've got 5 and then in parentheses x plus 2 and plus 9. What we need to do on this one is first looking at that x, we've got the plus 2. So that means you are moving to the left 2 units. And then the plus 9 used to be a plus 3. To get from 3 to 9, that means we moved up 6 units. So this last one shows a double translation where we moved both left and up. Go ahead and identify this translation on your own. In this case, you are moving you are moving right 5 for the negative on the inside, and then down 3 to get from 4 to 1. The other thing that we have to look at here is the dilations. Dilations are probably the trickier of the 2 types of transformations because we have to think about these both vertically and horizontally. So we're going to start with the vertical ones. This is multiplying the outputs. So this is changing the answers, changing your range. This is going to change the slope and the y-intercept. So if you're looking at y equals mx plus b, both the m and the b are going to change. So if we have f of x is equal to 2x minus 2, our first scenario is what we're going to call a vertical stretch. This happens when what you're changing by, your k value, is greater than 1. So in this case, it's 2 as my example. Opposite of that, if we do a vertical compression, it is going to be the k value is between 0 and 1, aka it's going to be a fraction. So what does that look like on the graph? So for that first one, that vertical stretch, I'm going to go ahead and simplify this expression, and I'm going to get g of x equals 2x minus 4. Notice, compared to the original, both the m, so it went from 1 to 2, and the b went from negative 2 to negative 4, changed. So what does that look like on the actual graph? So if I plug in 0 to this function, 2 times 0 is 0, minus 4 is negative 4. So your y-intercept is now at negative 4, and then you are going to go up 2 over 1. And then you're going to go up 2 over 1 again, and up 2 over 1 again. When you draw in that new line, you're going to notice that our graph is steeper than it used to be. So that's what it means to do a vertical stretch, is you're taking it and you are pulling it out like a rubber band. So pulling a rubber band up and down, it's getting longer, it's getting steeper as you pull it up. On the flip side of that, if we look at this second equation now, we've got g of x is equal to 1/2 x minus 1. So you plug in 0, half times 0 is 0, minus 1 is negative 1, so your y-intercept is now at negative 1. Then you go up 1 and over 1, up 1, up 1, and over 1, over 2 again. Up 1 and over 2 again. So now you have this new graph, which is going to be flatter than the original one that you have. So the slope is less steep than that original graph. So we're taking it and squishing it together. Think of pushing your hands together and squishing like a sandwich bun or something. You're pushing them together and you're compressing the bun up and down. So it's getting flatter as it goes up and down. So again, that vertical stretch, pulling it up, pulling it apart, making it get taller. That vertical compression, squishing it down, putting your hands together, making it flatter. Now on the flip side of that, we have horizontal dilations. This is multiplying only the inputs. So only the x's are getting multiplied by this new value. So what this means for your y equals mx plus b equation is that your slope is changing and your y-intercept, your b value, is staying put. So again, if we look at the original graph of f of x minus 2, a horizontal stretch is going to occur when our values are between 0 and 1. So for example, 2/5. A horizontal compression is going to happen when k is greater than 1. So x is equal to, k is equal to 5 in this case. Why is this different from the vertical? Let's look at that. So with our first one here, if we take and we multiply, we had that equation now, y equals 2/5 x minus 2. We're going to take that point, our y-intercept stays the same, and our new point from here is going to be up 1, 2 over 1, 2, 3, 4, 5. Then we're going to have another point, up 2 over 1, 2, 3, 4, 5. Notice the graph has gotten flatter vertically. It is not as tall as it used to be, but horizontally we have stretched it out. How do you know that? So if you look at that original blue line, it took us right now from 0 over to 4. It took us 4 spaces to reach a point of 2. In this new line, this 2/5 minus y line, it took us from 0 all the way to 10 to reach a point of y equals 2. So we took what used to be in this little red space and we stretched it out so that it's now taking up this whole green space. So that's why it's a horizontal stretch as you vertically compress a graph. Think about if you push down, stuff doesn't go away, it has to spread out left and right. So when you're pushing down and vertically compressing, that means you are stretching horizontally. Now, thinking about that other option where we had y equals 5x minus 2, and I said that that was a horizontal compression, think about our new points now. We've got still our y-intercept is at 0, -2, but now from there we're going up 1, 2, 3, 4, 5, and over 1. And then again up 1, 2, 3, 4, 5, and over 1. So again, thinking about this, we're now thinking horizontally. How much space does it take for us to get to a point left and right? In the original graph, it took me all the way from 0 to 10 to get up to this value of 8. In this new graph that I have, so this y equals 5x minus 2, it only took me from 0 until x is equal to 2 to get to that new space. So if you think about it, when you stretch something out vertically, when you pull it up and down, you're compressing it left and right. You're making it take up less space across as it's taking up more space up and down. So remember, a vertical stretch matches with a horizontal compression, and a vertical compression matches with a horizontal stretch. So now, looking at these dilation values in an equation. So for A here, I've got 9 times 4x minus 7. If you think about it, that's a distributive property. That's going to change both your slope and your y-intercept. If you are changing both the slope and the y-intercept, that is going to be a vertical dilation. Because our number is bigger than 1, it's going to be a vertical stretch. And when you're dealing with dilations, you want to talk about the scale, so exactly what is changing. So we're going to say scale of 9. Looking at the second one, our change only affected the slope. We went from -4 to -2. So now, because it's only affecting the slope, this is a horizontal dilation. Now we have to figure out by how much. To get from -4 to -2, that means we cut it in half, which means we multiplied by 1/2. And if we are multiplying by a half horizontally, that is going to stretch it out. Remember, if you push down vertically, it's going to stretch out horizontally. So half means a horizontal stretch. And then our scale on this one is going to be that 1/2 value. Instead of writing scale of, you could also, for these, indicate using k equals 9 if you don't want to say the scale. Or on this second one again, k equals 1/2. So you can use k as that value for what you are changing. Go ahead and identify this dilation on your own. If you look at it, you are multiplying both the slope and the y-intercept by 3, which indicates vertical. 3 is above 1, so it's a stretch, and your scale is 3. Last thing we want to do is identify the transformations based on a graph. So our original blue line is 2x plus 1. And it's asking us to find the k value to get to this red line. Notice your slope doesn't change. So it is going to be a translation. So we are looking for how it moved. Since the k is in the parentheses, we're looking for how it changed left to right. So I'm just going to pick out a point on the line, and it goes over 1, 2, 3, 4 spaces. I could have picked a point up here. 1, 2, 3, 4 spaces. Could have picked a point down here. 1, 2, 3, 4 spaces. Wherever you move, it is right 4, which means that your k value is -4. Again, remember, moving things to the right moves things down. That's why it is a -k. Go ahead and identify the k value of this function on your own. In this case, looking at the graph, you're changing something that is outside of the x's. So we want to, in this case, we're going to add 3. We're going to move that line up 3 in all places. If you have questions about this or anything else from the lesson, please let me know when you get to class.